Hi there. So this is a little short video just about applications of the force on a charge in the previous video. And this is like a simple version of mass spectrometer and how that works. So just a quick review, first of all, stuff from last time, the forces on a moving charge. We can use the amended right-hand rule, where the fingers are the direction of the magnetic field, the thumb is the direction of the velocity, the direction the particle's moving, and the palm would be the direction of the force on a positive charge, and the back of the hand is the direction of the force on a negative charge. So for finding the direction of the force, and the magnitude of the force can be found by going Bqv, magnetic field strength, times the charge times the velocity. And just to sort of what that looks like, we've got a magnetic field and we've got a particle of unknown charge, or it could be any charge, moving with a velocity v into a magnetic field. Now, if that is a positive charge, so using that right-hand rule, fingers pointing into the screen, thumb pointing to the right because that's the direction it's moving, palm is facing up, so there will be an upward force on that particle. That will make it deflect upwards. But as it moves, the direction of that force will also turn because the force is always perpendicular. So it will move in a circular path because the magnetic force is acting as a centripetal force. It's always perpendicular to the direction, so it makes it a circular path. If it's a negative charge, force will be in the opposite direction and it will deflect downwards, but again, you'll have that same circular path happening. And if it's a neutral charge, there's no force, so it will just move through undeflected. All right, so that's just a little quick review on that. Now, in terms of applications of this, a little bit of background about carbon dating. Again, this is very simplified. There's some big assumptions in here and things, but we're just going to sort of go through to get to the fundamentals of what the applications of the magnetic fields. So carbon dating is based on two isotopes of carbon, two different types of carbon, carbon-12 and carbon-14. Carbon-12 has 6 protons and 6 neutrons. That's the most abundant form of carbon on Earth. And carbon-14 is much rarer. It has 6 protons and 8 neutrons. 6 protons means it's still carbon, but the 8 neutrons means that it's heavier. So C14, carbon-14, is heavier than carbon-12. And another important feature of carbon-14 is that it's radioactive. That means that the atoms will occasionally split apart. And when it does that, it turns into C12. If you have a lump of carbon-14, it will slowly over time turn into carbon-12. Okay? Now, if we were to look at the proportions of total carbon, and we usually talk about the proportions in a living thing, because living things, you're eating food, and for a plant, it's taking carbon dioxide from the air. It's continually replacing the carbon in its body. Like in a human, the carbon is continually being replaced. So your proportions of carbon-12 to carbon-14 in your body stay pretty much constant because you're continually replacing it. But when the living thing dies, you're not replacing the carbon anymore. Okay? So all the carbon-14 that you have in your body, that's all that there's going to be. But it's gradually, over time, the amount of carbon-14 you have left in the body, or whatever it is in the living thing, is going to decrease once it dies. And that's going to slowly turn into carbon-12, which means the carbon-12 will gradually increase. Carbon-12 is very stable. Okay? Now, that may go on for like thousands and thousands of years until we get to, like, let's say that end point there is now. Now, if you can measure the proportions of carbon-12 to carbon-14, and if we knew what they were to start with, and we know that carbon-14 decays at a known rate. If we know the rate and we know the final proportions, we know the initial proportions, there's some big assumptions and some black magic that goes on in figuring out what the initial proportions were. But if we know those things, we can figure out how much time has elapsed from when the thing died until now. And that's basically what carbon dating is based on. But we need to know what those proportions are and how do we measure that. And that's where magnetic fields come in. So this is going to be a really simplified version. There's lots more complicated things of mass spectrometry, but essentially we take a magnetic field. I'm going to put some numbers on this. Okay, a 7.8 millitesla magnetic field, and let's say we were to fire a carbon nucleus. Now, carbon 12 nucleus, has a charge of 9.6 times 10 to the minus 19 coulombs. It's positive. We've stripped all the electrons off it, and its mass is 1.99 times 10 to the minus 26 kilograms. And let's say we fire it into this magnetic field at 6.55 times 10 to the 4 meters per second. Now, using the right-hand rule, it's a positive charge, so the palm facing upwards with all those directions means there'll be a force upwards, and it will curve upwards. Okay. Now, it's moving in a circular path, meaning there's a centripetal force, and what's providing the centripetal force is the magnetic forces. Okay, so we can actually calculate the size of that magnetic force. Okay, B times Q times V. We've got all those numbers there. Okay, B is 7.8 times 10 to the negative 3 because it's millitesla, so milli is the times 10 to the negative 3. The charge is 9.6 times 10 to the minus 19 coulombs, and the speed is 6.55 times 10 to the 4. That gives us a force of 4.90 times 10 to the minus 16 newtons. Now, that's a small force, but it's a very small particle. Okay. Now, remember that force being provided by the magnetic field is providing the centripetal force. So the centripetal force, which is mv squared over r, is equal to that force. Okay. Except what we want to find here is we want to find the radius. We know the force and the mass and the speed, so we can rearrange that to find r, which is mv squared over the force. And if we plug in the numbers we know, remembering to square the v, because that's a thing that's often forgotten in these calculations, it gives us a radius of 0.174 meters, or 17.4 centimeters for the radius of that curve. Now, the important thing, though, is that when we do this, not all of the carbon nuclei are carbon-12. Some are the radioactive form of carbon-14. That's 2 more neutrons, it's a bit heavier. So how would you calculate the radius for carbon-14? Okay. If you want to have a go at that, you can pause the video, and I'll go through it in a second. But if you want to have a go at it, have a go. But assuming you've had a go at that, here's what we do with carbon. So there's the carbon-12 calculation, the same from the previous one. If we do that with carbon-14, now some things are the same and some things change. Now, first of all, if we calculate the size of the force, B, Q, and V, it's still the same magnetic field. The charge is still the same because it's still carbon, and the speed is still the same. So those numbers are all exactly the same as before, so you get the same force. So the actual size of the force on the carbon-14 is no different than carbon-12. Okay? Which means the centripetal force is the same. But when we calculate the radius, the difference is in the mass. Okay? Because we've got a larger mass and the same speed and the same force, that means we're going to get a larger radius. Okay? So carbon-14 nucleus will have a radius of 0.205 or 20.5 centimeters, which means that it will move in a curve with a larger radius. So carbon-12 and carbon-14 will end up at different places. And if you have detectors there, you can measure how much carbon-12 there is and how much carbon-14 there is coming through, and you can get your ratios of how much carbon-12 to carbon-14 there is, and from that you can figure out how long ago the thing died.